Welcome, welcome, folks. So good to see you all here. Welcome, welcome. Good morning, good morning. So good to see you all. So happy to have everybody here. Welcome, welcome. All right, make sure to mute yourself as you come in. You should automatically be muted, but I am noticing some folks are unmuted, but go ahead and mute yourself as you come in. Thank you so much. So happy to see you all here. Wow, look at all these folks. This is so cool. Wow, I'm so excited to see everybody here. All right, getting everybody in the room. So exciting. Welcome, welcome, everybody. So good to see you all. All right, I think we have a good amount of folks, so I'm gonna go ahead and get started. Hey, welcome everybody to the Experimental Weaving Lecture Series. We're so excited to get started. We have 4 amazing talks for you this fall, and we're so excited to get this series started with Elizabeth. You are going to be, it's been such a wonderful experience. Of course, she was our former Weaver in residence, and Laura's going to give her a formal introduction in just a minute. As we welcome you all in, I just want to remind everybody, please keep your audio muted while you're on. Thank you very much for doing that. And if you have any other questions, feel free to private message me in the chat feature while the talk is going on. And if you have questions as the talk is going on that just occur to you, go ahead and put those right in the chat as they occur to you. And at the end of the talk, I will gather all those questions together and moderate the conversation with Elizabeth at the end. We're so excited to be joining from the University of Colorado Boulder this morning in the Unstable Design Lab. And it was with great pleasure that I introduced the introducer, who is my colleague, Laura Devendorf, the founder and director of the Unstable Design Lab. Good morning, Laura.
Good morning. So we're in a bit of a situation, right? I'm presenting here, but I also maybe want to turn it around. And this is my class. Everyone can say hello. So yeah, welcome to the first lecture we have in our annual Experimental Weaving Talk Series. Yeah, I just want to point out that this is being co-hosted with a class that's called Experimental Textiles. And so what's kind of interesting is today we'll be hosting the talk in the first half of the class. And then actually in the last half of the class, we're going to be doing some re-implementation of some of the concepts that Elizabeth is going to talk about. So like winding electromagnets. If you're curious about the course, all the curriculum is online at extx.unstable.design. But yeah, I'm really excited to welcome Elizabeth today. Elizabeth got to spend last spring with us as the experimental weaver in residence. And in that time, I just became, and I think everyone who had the pleasure of working with her became kind of enamored with her brain, which seems to be at once communicating with aliens that are also yarns. If you'll see in this talk, her design files and just the way she thinks about weaving and structure is really wild and inspiring and cool. We're just so thrilled for her to be here to share her practice. And yeah, I just want to turn it right over to Elizabeth. Thank you so much for joining us. And thank you all in the online world who joined us today as well. So I'll close my slides, Elizabeth, and you can go ahead and share yours.
Great. All right. Okay. Is everyone seeing what they need to be seeing? Okay, great. Thank you, Laura. So my name is Elizabeth Meiklejohn. I'm a textile designer and researcher, and I currently work as a textile engineer. And I'm happy to take questions about my professional work at the end of this talk. I was the 2023 experimental weaver in residence. So for 3 months this spring, I was working at the lab, developing fabric structures, samples, and eventually an interactive textile piece. When I first joined the lab, we had pretty broad ideas like sensing fabrics, actuating fabrics, and we gradually focused in on a genre that we felt was underexplored and ripe for experimentation. So first, I want to give you a sense of where this talk is going. I'll start by sharing my background and some of my research interests, and then the residency itself. It began with a sampling phase, which helped us identify an idea for a more polished, interactive textile artwork. So we went through a few rounds of prototyping before creating the final piece. And then lastly, I want to share some of the questions and reflections that arose from that design process and how we're moving forward with them. So this is what my textile design work looks like. Before coming to CU, I completed my MFA in textile design at the Rhode Island School of Design. The fabrics on this slide and the next few were created during that period, where I was focused almost exclusively on wovens. I came there with a background in digital fabrication and computational design. So when I started weaving, I really approached it as a way of additively building 3D structures. I think knitting is often referred to as 3D printing for clothing in this sort of colloquial, non-specialist audience way, but weaving also has that capability to place specific materials in specific layers and zones. There are just a different set of constraints that we work with. Not every fabric that I make is 3D, but a lot of them are. I'm also very focused on color phenomena and interactions, trying to make industrially produced materials feel ethereal and alive. So one of my primary areas of research is textile behavior, which I describe as the way fabrics move, perform, and react based on their physical properties. This includes behavior during the weaving and post-processing stage, like this loop pile fabric that shrinks when steamed, and behavior that happens when someone uses or interacts with the material. I'm interested in all of these potential movements, and I developed a lot of self-shaping fabrics that are woven flat and then morph into a specific 3D form afterwards. Understanding textile behavior, which is derived from yarn behavior and weave structure, allows us to design, predict, and repeat these specific forms, building a viable design methodology that more people can adopt. This is a simulation of a self-folding fabric in a tool that I built in Rhino 3D modeling software using Grasshopper and Kangaroo, which is a physics-based simulator. I worked with the Virtual Textiles Research Group at RISD to develop this design methodology, which was actually inspired by my own frustration when physically prototyping self-shaping fabrics and waiting to see how they transformed and how they turned out after cutting off the loom. If we can iterate on these designs before we actually weave them, which can be super time and labor intensive, we can move through the prototyping stage faster. But more importantly, we can also discover new design possibilities just by playing and experimenting with this new workflow, seeing what happens when we change different parameters and getting surprised by the results. This is a recurring theme for me, that developing new systems for design and visualization can facilitate new ideas. I really love working with complex weave structures, which is a good thing because it's hard to make 3D fabrics without them. Weaving, as I mentioned earlier, provides a unique opportunity to work on multiple layers and define all of the interactions between those layers. If you're strategic about which layers intersect and where, and which yarns weave on each layer and in what structure, you can get really dimensional results, like this 4-layer fabric that I'm showing here with 2 shrinking outer layers and 2 stiff, non-shrinking inner layers that zigzag between them, kind of like corrugated cardboard. This fabric becomes about 2 inches thick after taking off the loom and finishing, which is pretty unusual for a fabric that's woven flat. I'm showing a breakdown here of the weave structures in just one region of the fabric because I want to take a really deep dive into what's going on. There are actually no layer interactions in this specific region. Each of the 4 layers is woven separately. And I wanted to highlight that each weave structure itself is made up of multiple weave structures. This was built in Pointe-Carré, so that's what the screenshots you're seeing are representing. The outer layers, which is the lower left and upper right of that grid, these are actually a compound satin with 4 weft systems, 2 of which are warp-faced and 2 of which are weft-faced at any given time, so that I get a combination of 2 different colors producing that variegated blue and yellow pattern on the surface. Each inner layer is 2 layers of plain weave bound together with a tie-down, which is a very weird specific structure that was chosen for specific reasons, basically maximizing stiffness. So I use this strategy of compound structures feeding into more compound structures as a sort of shorthand. They're all named and labeled, so I can always go back and remember what each one is actually made of. This is another self-shaping fabric with a similar idea. There's a colorful pattern on the surface, and then there's the topography of the fabric that's formed when it comes off the loom and shrinks in the weft direction and wrinkles and buckles. This one has some elastic floats that are hidden between the layers. That's what's causing the physical deformation. I'm always thinking about this interaction of the 2D and the 3D form, both for the aesthetic and conceptual implications of my work. I want to make textiles that feel mystifying, naturally occurring, yet unnatural, almost like sensory illusions. And I'm thinking about the techniques that I need to use to actually weave these fabrics. Most of what I've shown here so far is woven on a jacquard loom. I rely a lot on color as a visual language, both to help me keep track of what's in my designs and to eventually communicate to the loom what needs to happen in each area of the fabric. I've been interested in color theory, digital color, and the math behind it for a really long time. And I really like that color is a variable with 3 data points or channels, RGB or hue, saturation, lightness. CMYK is fake. It's not really 4 channels for reasons that I can't get into now. But this is a 3-channel data point that we can store a lot of data in. So I use hue to indicate what's happening in the structure of the fabric. So the red, yellow, green, and blue stripes. Are layers separate or are they weaving together? What order are the layers stacked in? And I use value or brightness in this grayscale map to indicate what's happening on the surface of the fabric. What color fabric am I weaving from the combination of warps and wefts visible on the face? These 2 channels can be layered together with no loss of information to create a weave graphic and color palette with every possible combination of surface and structure. That's what you're seeing at the right side of this slide, this complex mapping. A unique weave pattern can be then assigned to each color. This gets complicated really fast. There are so many permutations of layer order for 4-layer fabric, just to give an example. I really enjoy this complexity, and I wanted to give you all a sneak peek into what that looks like when I'm going through this process from Photoshop to Illustrator to Python to Grasshopper, back to Photoshop to Pointcaré, and eventually ending up with something like this, unintentionally discovering the limits of the tools that I'm using. Another recurring tactic in my practice is hacking or modifying machines. This could be as simple as adding on a new tensioning system, like this first photo where I'm using clips and weights to pull on the selvages of an elastic weft fabric, or the middle image where I've inserted steel rods so I can independently tension several subsets of warp that are all coming off the same beam. It could also be as complex as replacing the shedding or warp lifting mechanism. In this model, which I later scaled up to my actual loom, I added a set of rods that lift the warps based on the topography of the ground. I do all of these things because I want to push these machines to make fabrics that loom designers and engineers never envisioned. In the last example, I wanted to push my 4-harness loom to weave large-scale jacquard-style patterns, and I wanted the pattern input to come from a different data stream than what the weaver drafted or pressed with their feet. There's an attitude towards machines that I find really beneficial in these cases, not being afraid to drill holes and bolt things on, at least for machines that you personally own, and understanding tools for what they physically, objectively do, rather than what they're intended to do. So this brings us to the beginning of my time at the Unstable Design Lab. Laura and I had thrown around a lot of ideas for getting started, and I pursued a few of them while also making some tried and true multi-layer structures, things that I was familiar with, just to see what arose from experimenting with them in a new context. We talked about building a collection of low-profile force sensing fabrics. So I tried some inlay and pile weave with conductive yarns. I had also listed out a whole suite of techniques for making actuating fabrics. Previously, I'd made a lot of fabrics that change shape once and irreversibly, like these self-folding fabrics. but I wasn't as familiar with fabrics designed for continuous repeatable motion. Some of my favorites were these stretchable and collapsible structures, like the light blue and the white example in the top row. And the top right sample, which doesn't photograph well at all, but has 2 layers that can slide sideways relative to each other. This was actually the very first sample that I wove on the TC2 loom at the lab. I had made this style of self-folding fabric with these accordion pleats before, but I wanted to combine it with some additional surface features that could move back and forth. Not really thinking about applications at this point, just fabrics that move. Typically, when we weave a fabric, the weft yarn moves edge to edge. And when we weave multiple layers, each layer covers the entire area of the fabric, right? It had never occurred to me to break these rules, maybe because I never had access to a jacquard shuttle loom before. On a shuttle loom, your edges are always clean and your weft is always moving in a continuous path back and forth. And on a jacquard loom, you can lift an arbitrary set of heddles in the middle of the fabric instead of across its entire width. I sketched a design for a base layer with 3 sets of flaps, like little books, and then mapped out how the weft would need to travel to visit all of those layers, kind of like a little traveling salesman. Again, I'm relying on color in this diagram, in this case as an indicator of time passing. So the weft path fades from white to black from start to finish. The rainbow colored arrows show what sequence the steps occur in. Let me just move the Zoom UI out of the way so I can read the rest of my notes. I converted these arrows to another form of graphic representation. And I think this is the point where Laura came up to my desk and asked if I was communicating with aliens. This was a style of diagramming that I had never worked with before, but this was the precursor to turning this initial idea into a weave draft and eventually into a fabric. Here's another way of demonstrating what's actually going on in that fabric. So the shuttle is taking this circuitous path, sort of a forward 3 steps, back 2 steps, and so on. And it's covering all the ground that it needs to in order to make this cross-sectional shape. Most pieces of fabric just have 2 vertical edges, but this one has 8. It's kind of all edges all throughout the fabric. You can see in this photo that only the center warps are raised, and where the weft yarn is positioned, I'm about to weave from right to left. We referred to this technique as partial weft weaving or partial weft passes, and we certainly didn't invent it, but it's something that we really built a methodology around during this residency. I became pretty confident that any cross-sectional shape could be woven with this method, as long as the weaver was willing to put in the time. I've been fascinated with spacer fabrics for a while, which have a large air gap between layers, but I've never had access to the right kind of machinery to make them the way they're actually made industrially. So this is sort of a pseudo spacer fabric that's woven flat on the loom and then springs up into a 3D form. It has this interesting scissor joint motion that got us thinking about other mechanical linkages and how to make them work in fabric form, because fabrics are usually pretty soft and can't transmit motion. The method of diagramming with arrows continued to work really well here, and I'm showing the weave draft in the center here with the multicolor weave graphic overlaid onto it. There's a lot of negative space, so no warps lifting, and that's characteristic of these partial weft drafts because we're only weaving one section at a time. One way to think about it is the thought process is first determining which region gets woven in any given pick, because it's not going to be the whole fabric, just one little area. And step 2 is deciding what actually gets woven during that pick. Is it the base layer? Is it a middle layer? Is it plain weave, twill? So that will get filled in on the draft. And here's one more fabric from the sampling round. This one doesn't use the partial weft technique, but it's still plenty complicated. It's a 4-layer lattice with elastic floats running through the middle. So in this cross section, you can see that each layer travels from the top of the stack to the bottom in this repeating unit. The weave graphic is actually really simple, just vertical stripes. So working from left to right, whenever the layer order changes, the color in the weave graphic also has to change. So we end up with this diagram, as we often do, working with rainbow hues that looks like a pride flag from the future, which I really enjoy and find kind of beautiful. But this also makes it a lot easier for us to understand what's actually going on. You can see that this weave draft is not an effective way of describing what happens in the fabric. So something's happening in each vertical section, because we can see that the vertical sections are different, but we can't actually tell what it is. The cross-section and the written layer ordering are much better ways of documenting the design. There are also some important fabrication instructions that aren't contained in the weave draft. This design is made specifically to have nice, clean, tubular selvages, but that only works if you start with the shuttle on the left side. You also need to pull the elastic weft tight when inserting it. So where should all this information live? At the same time that I was developing this visual notation system of arrows and time and order of operations, we were spending a lot of time talking about electromagnets. This is something a lot of us learn in elementary school science class. You wind copper wire into a coil, run a current through it, it becomes a temporary magnet, and you can use it to pick up paper clips. Magnetic attraction and repulsion was one of the forces we were interested in for powering an actuated textile. And being able to turn a magnetic element on and off or reverse its polarity could allow us to program and animate the fabric to move in a sequence. There's also just something that I found poetic about the path of the coil relating to path of yarns in fabrics, and the challenge of building a coil within the logic of weaving. Weaving is a little bit like Tetris. So once you insert a weft, you block off all the areas below it, and you can't go back and weave more in that area. How can we weave a spiral which returns to the same spot over and over? These were a few proposals that I designed, trying to stay within the rules of weaving and express these weird tricks and moves in a way that others could understand. These examples also explain why we spent so much time on coils. It's just exciting to see this movement, right? Even with simple paper prototypes, we were getting pretty clean, repeatable actuation by turning a coil on and off. This model was based on the pseudo spacer fabric. So can we get those cells to snap open and closed? What if we build a crease into that vertical wall? Some of the lattice structures also had that flattening, opening up potential. There's a whole other range of motions that you can power with electromagnets. We came across a paper that described a really elegant solution for continuous linear sliding, which is hard to achieve when your only available actions are turn magnet on and turn magnet off. In this case, there are multiple coils being powered in a specific sequence. There are also magnets that are magnetized across the diameter instead of through the thickness, so they flip over rather than traveling towards or away the electromagnet. We were also inspired by the work of Irena Posh, who Laura had worked with before, and who ended up being a collaborator on our final piece and the whole process of creating it. Her work, The Embroidered Computer, uses these really intricately embroidered electrical connections and coils to flip magnetic beads and actually functions as a computer that can perform calculations. We tried so many different coil making methods, winding by hand, with shuttle passes, as a tunnel between layers of double weave, using a bobbin winder, different sizes and shapes of objects that we were winding onto, different core materials. And we eventually set aside the idea of forming the coil on loom because it just wasn't practical. To increase the magnetic strength, so to attract a heavier object or something that's further away, we needed to increase the number of turns in the coil. The top right example, which is wound onto a tapered form, so most of the coil footprint is filled, that was the one that performed the best in our trials. I also want to step back for a minute and talk about how to achieve fabric actuation. I read a lot of excellent papers on soft actuators and various methods of making fabrics move, from shape memory alloy or SMA wire to pneumatics to motors and magnets. What all of these examples here have in common is a base fabric structure that amplifies or transforms the motion of the actuator into motion of the entire piece. So the yellow pneumatic piece, for example, if you have a tube of fabric with a uniform structure and you place it over an inflatable bladder, the whole thing just inflates, not super exciting. What the researchers did here is specify a zone which is a little bit darker yellow that has a different fabric structure that's less elastic. So when the bladder inflates, it affects that area to a lesser degree. All of a sudden, we have non-uniform inflation, and we have this really cool bending action. The flower example that uses SMA wire, which has a pretty short actuation distance, how much it shrinks when heated. But if you knit it into a fabric, it wants to become a straight line when heated, returning to the state that it has a memory of. And that distorts the knit loops to be very short and very wide, so the fabric petal is significantly transformed. And the origami crawler is another great example of form and repetition amplifying a small initial actuation. We were really excited about the uniqueness of the partial weft weave structure and the ability of these surface features to occupy different states, to flap back and forth or stick out from the fabric. And this also led to interesting visual effects with light and shadow that we started to see in sewn prototypes. So this would be the base fabric structure that our actuators would bring to life. I want to take a slight detour at this point to talk about color and color phenomena. Here's this effect that I was familiar with in a few different contexts. There's this childhood game where you hold a buttercup under your chin, and if your chin turns yellow, supposedly it means you love butter. Of course, it does that to everybody. It's just the petals bouncing yellow light onto your skin. And there's actually research showing that these specific flower petals are incredibly good at reflecting light. So that's one example. Robert Rauschenberg also did a whole series of sculptures where the backs are painted with fluorescent pigment, and they're always installed really close to a wall. So you never actually see the bright color, but it looks like the whole piece is glowing. And then on the plane ride here to Colorado, the person in front of me had this bright pink jacket and it lit up the whole window well. I love all the way that these look like there's a light source emitting colored light, but there is no emitted light. Nothing is powered or plugged in. It's just reflected light from this static object. So of course, I grabbed some fluorescent nylon ripstop that was left over from a previous unstable lab project and got to work. These cut and sew prototypes are a really fast and effective way to mock up design concepts and see if the effect I was aiming for was actually possible. And as it turned out, it's extremely possible. These instances don't represent the physical properties of woven fabric, as we'll find out later, but they demonstrate one key aspect of the design, that a fabric with hidden colorful elements can appear to have a bright glow, even when the viewer can't directly see any of that colorful fabric. So this orange color that you're seeing is just the reflection of light hitting hidden orange flaps. Another important aspect of the design that needed to be validated was that the fabric had a state in which it appeared white or colorless, right? We need to be able to get the colorless state and the colorful state. We also need to animate or transition between them in a way that is visually compelling and rhythmic and mysterious. So causing the flaps to open without revealing the source of color, and ideally without revealing the actuator itself. We don't want to see a motor or a pulley. That was the goal here. I set a lot of these constraints based on the conceptual direction for the piece, which came from observing things like flickering light through windows and shadows of tree branches and scattered clouds, this soft fade in, fade out continuous motion that was very irregular and spontaneous. I loved the idea of making a fabric that gives you a sense of looking through a window or a dappled body of water, just watching the light flicker. So this is a very simple gesture that shows where we're heading with actuation. If you let the flaps naturally open, they're orange. If you press them shut, they're white. This is also the first woven prototype of this design, and the orientation that you see in this photo is how it was woven on the loom, except that the flaps were open while weaving. That's what causes them to have a bit of a bias towards being open, the way that they were arranged, and also because they were woven with monofilament, which is notoriously stiff and stubborn to work with. This prototype is also sort of like 5 prototypes in one, because I was constantly stopping, evaluating the fabric, editing the weave design, and then continuing to weave more of the piece. You can see the transitions from one design iteration to the next, and I want to do a bit of a deep dive into that. So these are the first 3 design iterations I tried out, really pursuing the goal of maximum orange with minimum effort. A really simple way to increase the orange appearance of the fabric would just be to use more orange yarn, right? Either by winding more strands of it onto a bobbin or by increasing the pick ratio of orange yarns to base yarns. But I felt like I was already using a good amount of orange yarn. It just wasn't operating at its full potential. These diagrams are a little simplified, but in the first 2, starting from the bottom, I wove a plain weave base with the orange as a supplemental weft that interlaces with the base warps in a satin pattern. The only difference between the bottom and the middle examples is the length of the satin floats. You can see that the longer floats are giving slightly better coverage on the surface of the fabric, but inherently with this structure, the orange yarn is getting pulled down into the base instead of lying flat and straight on the surface. Anytime we have these yarns bunching together, we have blank spots that the yarns are not covering. A much better approach is to weave this as 2 layers, where the upper layer has a few warps that are sort of donated from the base layer that the orange yarn interlaces with. These donated warps need to periodically rejoin the base layer, and then a different set needs to start weaving with the orange. I call this warp rotation, just to maintain even tension and to periodically bind the layers together, because the orange layer has basically no structural integrity. It's just very loosely woven. Ultimately, this achieves the goal of covering as much of the fabric as possible with this highly pigmented yarn. In the second prototype, I applied all of these learnings about weave structure. There were some more tiny improvements, like getting the neon to not show through at the hinge of the flap when it's closed. You can see a little neon yellow mistake there. I also experimented with color blending by using weft stripes of different colors, basically any fluorescent or super saturated colored yarn that we could get our hands on. I also want to point out that at this point in the prototyping process, the weave structure was getting all these small refinements and improvements and was also getting massively more complicated. What we're looking at right now is the multicolor weave graphic, and that is the precursor to the weave draft. So once this graphic is created, a different weave structure is assigned to each color. This is a modified file for the fabric you just saw with only 3 flaps. And the number of colors and what they all represent has grown just exponentially since the first prototype. I was keeping a super detailed page of written notes, like the darkest shade of indigo means the neon floats under the hinge. The lightest shade of indigo means it floats over everything. Just a lot to keep track of here. And this is where we reached some key decision-making points in the design process. A pretty straightforward one was integrating the coils. Laura had done a lot of previous work routing wires and conductive yarns through fabric by carrying them along as supplementary warps or wefts, and that worked really well in this small-scale trial. It was the first time I had used that technique. This was the first test of on-loom coil integration using the approved coil design. I'm using cut-up boba straws from the cafe downstairs as bobbins for the copper wire. I went through a big bobbin lace phase several years ago, and that really prepared me for this. Another issue was the ability of these flaps to actuate the way that we wanted them to. The loom has a cotton warp that can't be changed, so to add a sort of papery stiffness to the fabric, I was using linen and silk and other stiff weft yarns. This brings up a key property of woven fabrics. They're often anisotropic, meaning they have different physical properties along different axes. The fabric has high stiffness in the weft direction and low stiffness in the warp direction, meaning it can bend easily along the length of the flap, which is not good. And it also resists bending where the flap meets the base fabric, also not good for our purposes. What we really want is a flap with lengthwise stiffness and a soft, malleable connection to the base so that it can easily flap open and closed. So can we take this prototype, can we take the fabric properties and just rotate them 90 degrees? Kind of. This is sometimes called railroading a fabric, where the whole design is just rotated by 90 degrees. often so that it travels along the length of the yardage instead of across the width. With traditional jacquard and dobby patterns, this is very straightforward. You just rotate the weave graphic, maybe make some adjustments for the aspect ratio to account for picks per inch and ends per inch, and then just input the same weave structures. The reason that this works is because the warp and weft are not really that different from each other in the finished fabric. They both go over things and under things, and they go all the way to the edge. If you looked at a cut section of this fabric, it wouldn't really be that meaningful which yarns were the warp and which yarns were the weft. But in our fabric, the weft is behaving in a way that only wefts can. It's traveling in loopy paths, and it's not going edge to edge. We can't just rotate the design and ask the warp to follow these same paths because it's constrained at both ends. Instead, what I ended up doing is overhauling the entire design in order to weave a structurally similar fabric with the flaps oriented along the weft direction instead of across it. My notation system shifted too. So this is a cross section looking at the vertical edge of the fabric rather than the horizontal edge. We're looking at it from the side of the loom, basically, instead of head on from the front of the loom. And there are no more back and forth arrows. The shuttle will be moving all the way from edge to edge. We can think of the old design as a vertical extrusion and this new design as a horizontal extrusion. And the weave draft looks pretty different too. The negative space that we get with partial weft drafts is gone, and we get something that looks a little more normal. The thin stripes are where I'll be adding a magnet between double weave layers. But the coil locations and wire routing aren't marked in the draft, so it's up to me to put them in the right spot. I'm really glad we have this footage of the whole weaving process because it shows details that would be easy to forget or hard to explain. I'm a big proponent of mise en place, this French culinary term for having everything in its place, your ingredients, your tools, everything at hand. So I've prepped all the coils in advance on a little sheet of cardboard, and I've brought them to the loom. I'm also following along with the weave draft on my laptop so I can keep track of where I am in the file. I know when something's about to change or when I need to put a coil in. The machine doesn't prompt me for these things, so I have to look out for visual cues. There are some sub-steps that are so granular, I didn't even plan for them ahead of time, but I developed them on the fly, and then they become part of the formalized process. So I'm taping down the coils so that they don't bounce around and get damaged by all the repeated packing in the wefts. That's something that you really only learn from experience. As the piece progresses, there are more and more wires to manage, and the draft doesn't indicate this. If you look at the draft, it just looks like the same repeat 4 times in a row. But what's happening in reality is another story. You can also see that I'm taking breaks and reevaluating, having conversations with people. Stephen brought their dog into the lab. It's all part of that 3-day sprint to weave the final piece. This fabric is also unique from the earlier prototypes because it requires more post-processing. The warp is continuous, basically by definition of what it means to weave. So it runs through areas that need to be separated. I cut the warp floats and pulled their ends through the base layer to free each edge of the flap. The wires also needed to be routed along the selvage and top edge of the fabric. To be honest, this was not planned until I started doing it on the loom. It's something that was hard for me to envision until I was physically doing it, moving the wire bobbins around. What ended up happening is somewhere between pre-programmed and improv. I followed the 3x1 twill structure of the base fabric, looping each wire around its designated warp whenever that warp was lifted. I'm still thinking about how to formalize this technique, which somewhat breaks the rules of weaving, but also relies on them. Finally, the most nerve-wracking part was making 16 good, secure electrical connections to wires the size of a hair. We couldn't solder to it or use crimp beads, it just kept breaking. Laura really shepherded me into electronics by emphasizing that connection is just about physical contact, and that was a really good way for me to understand this. So we ended up using more of a soft connection embroidery technique by lashing the copper wire really tightly to an exposed stranded wire, and that ended up working beautifully. The final piece is titled Magnetic Reverberations and is a collaboration between myself, Laura Devendorf, and Irena Posh. It was recently on view as part of the Textile Intersections Conference in London. If anyone here was able to attend, I hope you enjoyed it. I really wish I could have gone there in person. So there are 16 electromagnets and 16 permanent magnets. Each electromagnet can be powered independently to close the flap, which swings open again when the power is off. Laura programmed a web interface to control the fabric through touch gestures. This piece addresses a lot of concepts that were important to me, creating an almost analog color changing fabric, so without thermochromic inks or RGB LEDs, just harnessing a natural property of light. If its movements are repeatable and controllable, but it's also something that looks a little organic and natural because it can be played live and do this spontaneous fluttering motion. It's also a case study for this category of complex multi-layer structures and the design interventions that are necessary to construct such a piece. The hardest part is done, but this work emerged from a line of inquiry that we're still following. Reflecting on the processes we used to create this piece, as well as the final outcome, led us to a whole bunch of questions. Do we need a different data structure than the weave draft so we can fully document this work? In a similar vein, if we document the work well enough, does that ensure that it can be recreated? We know the design process is iterative and we discover new methods by doing. How do we return to the documented design, even the final V2 design, and incorporate what we learned? And when it comes to incorporating elements like coils, these had some yarn-like characteristics and behaved like yarns, but they also bent the rules of weaving. What notation would we use for these movements? This is my last slide. All of these questions lead us towards the topic of design bookkeeping, which is a term that I picked up from a jacquard weaving professor of mine. We use it to describe everything that was done in addition to the usual design and drafting steps to maintain continuity of information. I always want to configure my work so that someone else could make it or restore it, so that I can look back and re-understand why certain design choices were made. There are so many important steps that happen outside the weave draft, steps that define notation, whether you call them marginalia, choreography, improv, outside text, actions happening off stage or off script. They're not trivial. We want to formalize these steps so they can be understood as equally important parameters of fabric creation, just like weave structure. Concepts like version control and bug fixes in software, the principles of art conservation, and the way that choreographed dances are written down on paper are all highly relevant and exciting to us. Borrowing techniques from other fields can enable us to build richer design methodologies that in turn enable the creation of complex and unprecedented textile works. Thank you so much for your attention. I'd also like to thank many people from the Unstable Design Lab, the CU Atlas community, and beyond that supported me in a whole bunch of different ways throughout this residency. After completing the residency, I moved from Boulder to the Bay Area, where I currently work as a textile engineer for Unspun. That's a technology company working to reduce waste and emissions in the fashion industry through 3D weaving. So I'm no longer the experimental weaver in residence, but maybe an experimental weaver at large. You can find me on Instagram or visit my website for all other links. Thank you again, and I can answer any questions.
Let's give a big round of applause. Hearing a round of applause, I think, can somehow maybe lessen the strangeness of a virtual. But if you are online, one of the things I like to do is maybe just write a quick word, say hi, let us know that you're there. Thank Elizabeth for this beautiful talk and the beautiful work. We did kind of document and create a whole catalog, which we're still in the process of finalizing and printing. There's also a description, written description of this design process on the Unstable Design Lab page. If you can't get enough of flaps and colors. Yeah, this has been really great. I want to turn it back over. Actually, can I just take a moment? Irena, would you just unmute and say hello, since you were so influential in the project as well.
Hello. Of course, happy to. And I'm like super happy that I had the chance to follow your talk today, Elizabeth. It was really nice because we never really met in person, but we always had this online collaborations. It was really nice to hear you present your work in your words and this whole journey that you've been on in the Unstable Design Lab. So thank you so much, and it's been an honor to be invited to take part in this journey.
Thank you, Arena. We'll meet in person one day.
Absolutely. Copenhagen.
Sorry, I realized something happened with my camera, so I selected a different one, and apparently the room we're in has a camera. So you can kind of see I'm here waving my hands, and you can see maybe the first row. But yeah, I want to maybe turn it over to Stephen for a bit of Q&A. I'll tell you in person in class, we'll have a little time after we sort of close the call to ask one or two more questions if you have one. Okay, so Stephen.
Hey, Laura, thank you. And Elizabeth, thank you so much for your talk. That was wonderful. Your slides were absolutely gorgeous. I'm going to bother you again, maybe hire you to do my slides for me in the future, if you're available with all your free time. I'll be like, could you just do this for me? That was a beautiful explanation. I love the documentation as well. There's a few questions in there, but I'm going to encourage folks to drop their questions, conceptual, personal, whatever questions you guys have for Elizabeth. Please drop those right there in the chat, and I will moderate those for all of us. Elizabeth, I just wanted to talk a little bit back to, we had a quick question about the double weave process that you use to create those flaps. And they were asking, like, if you had to explain that in the most basic way about like what exactly is happening there, could you do it? After you just spent this complex amount of time illustrating it, doing it, is there another way that you would maybe explain like what exactly is happening with the opening flap just segment? We had a question there online.
Yeah, I think so. I think that I might even explain it by moving away from weaving a little bit and just thinking about the path that an object is tracing. That object, in this case, is the shuttle carrying the weft yarn, but we can zoom out from that a little bit and imagine that we're just tracing a path. Maybe we're drawing it on paper, or maybe a 3D printer extruder is following a certain path, right? So if I want to make a specific 3D shape, I'm looking at the cross section of it, which is just a 2D shape. And I just want to trace all around the perimeter of that 2D shape. So it kind of becomes a question of looking at a shape, looking at all of the features and the flaps that come off of it, and thinking about, if I'm, an ant traveling along a line on a piece of paper, how am I going to cover every point along this line? So there's a lot of related problems in math, right? Like sort of network problems and as I mentioned, famously, like traveling salesman problems, which is not my background at all, but it's sort of something that I'm recreationally interested in. So I would describe it as just finding, for our purposes, the simplest and the fastest way to traverse that shape in the fewest number of moves, almost like a little game.
Oh, thank you. That was a beautiful explanation. And I just want to say, I love the poetry of what you're bringing to these like technical kind of like explanations. There was just something really beautiful about thinking through that idea of the refracted light and the reflections. And it's such a technical feat. I don't know if you had more thoughts about that, the poetic nature of the piece that you made. I've watched that video like umpteen million times. Like just it has ASMR brain effects on me. I'm not sure why. It's just so fascinating to watch, and also that beauty of the refractive light. I mean, do you have other thoughts about maybe just like creative and or extended my fashion applications that you'd love to see come out of this project?
Yeah, that's a really good question. I think I definitely agree with that ASMR take on the piece. I also see it as being very soothing and kind of enchanting and fascinating to watch, the way that a lot of people just like to sit in front of the fireplace and just watch the fire crackle and flicker. I think there's something that can be very mesmerizing about it. The sound of that piece is also really amazing. I didn't have sound on for these videos, but you get the copper coil kind of hitting the magnet and you get this muffled thump because there's fabric in between. It kind of sounds like rain falling on a roof, which is really amazing. So there are all these elements. I think the rhythm and the pace that they're happening at is dictated by the person who's playing the piece, right, through the touch screen interface. So it can be very composed, you know, like a piece of music, or it can be very random if they're just hitting all of those buttons. So some of the experiential qualities are really up to the person who's playing it. Or something we talked about in the future is connecting this piece to a different type of data stream. Like, can we look at the wind speed at a particular location, and can we feed that into, you know, like a binary on and off sequence for each magnet? Can we look at some other stream of data like radio waves? And that could be another future implementation. We were thinking of this pretty much as you know, a wall-mounted piece or an installation piece. I really wanted to create something that felt like a little window into another world. Haven't thought about it for other applications like wearables, but you know, all of these methods are documented pretty well. I would love for other people to run with these and just see what they come up with.
Yeah, I'm so excited thinking through the kind of different applications, the ways in which it could be like a data visualization tool. It just, there's so many open paths to like what that could be. So I'm so excited. Thanks so much for that work. Another question yeah, the idea of it being played. Yeah, Laura's like exactly right. And I just like imagine it like thinking through like visitors to a museum or footsteps or like what other like data could really like animate it. And also when if it was scaled up, just thinking how it could really just be just it's already such a fascinating object, to thinking of the other applications. Another kind of question for you, and I'm sorry, I'll be the artist in the room and ask these questions. There is such a performativity to the weavings that you make, and then also just knowing the way that you alter looms, the way you think about the loom as just this totally permeable tool. And I just love that. I love your mind when you like step into it. You're just like moving outside of those limitations. How do you think about the performance of the objects that you're making? I mean, some of your past pieces, and is that a huge relation for you? Because I think, you know, you're working sample size, right, most of the time. How does it like the pieces just have so much life, so much personality to them? I'm wondering where that occurs to you in your practice.
Yeah, I think for me, you know, the best case scenario is that people get to touch these fabrics and interact with them, you know, especially the ones that have these sort of three-dimensional, compressible, stretchable qualities to them. Even if they're just textile samples that aren't made for a specific application, they are really meant to be touched and interacted with. That was something that was constant, you know, the whole time I was in my MFA program, which was difficult because it was during COVID and no one wanted to touch anybody's fabrics. And so that was a really crucial thing for me. There's this great show that's at the Cooper Hewitt right now on Dorothy Liebes, who is this mid-century textile designer, weaver. And there's a quote from her that's like, "When people don't touch my fabrics, I feel personally hurt," or something. And I related to that so much. I would really love for these fabrics just, yeah, like you said, to be able to perform on their own when they have that actuating capability. But this is really the first piece I've made that truly performs on its own without someone physically touching it. A lot of the other ones that I've made, like, you need to sort of squish your hand into it or stretch it to get the full gist of what makes it really special.
Oh yeah, I love that idea. It's so funny, and I think there's a lot of textile people here in this chat this morning, and it's so funny when you exhibit textile work in a typical museum situation. It's unless you're explicit to allow people to touch it, they're going to touch it anyway, and I feel like that's like the sneak of that work. So it's really funny relationship, and I love that you're building that into the structure of the objects that you make. Any other questions? All right, well, I'm going to end our public portion of our talk this morning, Elizabeth, and thank you so much for being here. I'm going to drop the links again in the chat for people that are interested. Link to Unstable Design Lab, where they can come and check out your reading. And also to remind folks that we have Patricia George on October 25th. We'll see everybody here at 9 a.m. Once again. And of course, if you have any other questions, please shoot us an email on or an Instagram message, and we'll be happy to answer your questions for the Unstable Design Lab. All right, I am going to switch this over. Can we get one last round of applause and claps for Elizabeth? Thank you so much for joining us.
If you move to the front, you can be visible.
I'm gonna kick y'all out of this chat, and we're gonna hand it over to Laura's classroom. Thank you, everybody.